Hello and welcome. Today's presentation is brought to you by Science Visualized, where we're looking at organic chemistry, and this is Organic Chemistry Review, Part 3B. The first question says, provide the products for the following reactions and be careful to show the stereochemistry of the final product. And here we're looking at what's called McLafferty rearrangement, which is found in mass spectrometry. So in order to carry out a McLafferty rearrangement, you have to label the position starting from the carbonyl. This is a rearrangement that's shown by carbonyl systems. So the first carbon, after the carbonyl carbon, so that's the carbonyl carbon, that first one is alpha, the next one is beta, and then the next one is gamma, and then you have omega. So if that gamma position has a hydrogen here, then that system will undergo McLafferty rearrangement. And in McLafferty rearrangement, you use the lone electron pairs on oxygen to obstruct that proton. So it pulls that proton. Then let me redraw the product here. Then you have that carbonyl. And then here you have the next ring. And what's happening is that now the oxygen obstructs a proton. And because of that, the bond electrons, that's two electrons, flows there to form a double bond. So you end up with a double bond there. At the same time, you break the alpha-beta bond, so the electrons move there to form a double bond here. And then at the same time, the double bond to oxygen will have two electrons move to oxygen to restore the two electron pairs. So in that case, we remove that double bond from oxygen, and now we reintroduce the electron pair. And remember, we broke this bond here, so that bond is broken, and that's going to be the product of McLafferty rearrangement. So you end up with an alcohol and an alkene. This rearrangement will occur in aldehydes, ketones, esters, amides, basically systems that contain carbonyl groups. Question 2. It says, looking at the structures below, circle the most acidic structure. Remember, when you say acidic, we're looking at the ability to donate protons. So basically, we're talking about Bronsted acids. So Bronsted acid or Bronsted-Lowry acids. If you look at this structure A, it can donate that proton. So this is an alcohol, can donate that proton. Structure B is a carboxylic acid, and it can donate that proton. Generally, carboxylic acids are more acidic than alcohols. And the reason for that is that carboxylic acid have pKa of about 4, while alcohols have pKa of about 15. The lower the pKa, the stronger the acid. Remember, pKa equals to minus log of Ka, just like pH equals to minus log of the concentration of hydrogen ions. So this means then that when the value of Ka goes up, stronger acids have higher Ka because they release higher concentrations of hydrogen ions. But now the pKa is minus log of Ka, the pKa will go down. So that means stronger acids have higher Ka and therefore lower pKa. Weaker acids will have lower Ka and higher pKa. So explain why we chose B as the answer. And the first explanation is that B has a lower pKa and a higher Ka, making it a stronger acid. The other explanation is to consider the conjugate pairs formed. So if you look at the carboxylic acid, if it loses a proton, so it loses this hydrogen, you end up with a carboxylate ion, and that's called carboxylate ion. Compare that to A, where you're starting with an alcohol, and then again lose a proton, and now you end up with what's called alkoxide ion. Carboxylate ions are more stable because you can draw resonance structure. You can move those that minus charge or 2 electrons to form a double bond, and then you move this other one there, and you end up with a new resonance structure. Nothing is happening to the ring. But now that oxygen now has a minus charge, while the other one now has a double bond. And because of that, you're constantly distributing the minus charge between the two oxygens, and that results in a more stable structure. Anytime you can draw a resonance structure, you end up with a more stable structure. The more the resonance structures, the more stable that structure is. Compare that to the alkoxide ion, where this minus charge is not distributed. It's localized on the oxygen. And because of that, it's not going to be stable. So because carboxylate ions are more stable than alkoxide ions, then that means carboxylate ions will form easier and fast and quickly. Anytime the intermediate forms easily, if you look at a reaction diagram, so that's the reaction progress, and then here say energy. Then you're comparing two reactions. One has higher activation energy to give you product, and then another one has lower activation energy to give you product. The one with the lower activation energy will be faster. The reason for that is because you can easily attain the lower activation energy, and that's the same thing with the carboxylate ion. It forms much faster, making it more acidic, making it easier for carboxylic acids to donate protons. Thank you very much for your time. If you enjoyed this presentation, please support the channel by subscribing.